Thank you for the clap. Welcome back, everybody. This is the key to section 6.8 homework, page 463, 464, 1424. The transformation homework. Remember those transformations that we learned yesterday? They weren't brand new, right? They're just the transformations that we had before, just applied to polynomials. Remember, anything horizontal, I think you guys have found anything horizontal is a lot harder than something vertical, especially if I shift something left or right. Right? That is the hardest type of transformation to do with a polynomial. Shifting something left or right. I know, so inconspicuous. Like, oh, it should be easy, but no, it's not. It's pretty difficult. Shifting something left or right. Oh, be serious, everybody. Don't relax. We can relax today. So again, shifting something left or right is the hardest one to do, just because you have to, FOIL it all out. So, but here are the answers for 14, 15. I'll scroll down to see 16, 17, 18, 19. Again, you did not need to graph any of these things. The graph is just kind of like a sketch. If you wanted to sketch it, you can do so. So you can confirm the type of transformation that happens. Number 14 is x to the third minus 7. Just subtract the 3 down there at the bottom, or down there at the end. Number 15 is minus 4, so just subtract the 4. No, I lied. That's a right 3, excuse me, a right 3. So you're going to FOIL that out and then subtract the 4, excuse me. Here's 16. Let me scroll down and see 16 real quick. Looks like that one is an up 5. An up 5. So you take x to the third minus 4 and then just plus 5. So it should look like x to the third plus 1 at the end. Okay. And then scrolling up there to see 17, 18, and 19. See if we can get it almost all on the same page. Number 17 there, negative f of x, that's a reflection over the x-axis. So the negative goes to all parts. Remember, when the negative goes to all parts, that's a reflection across the x-axis. When the negative just goes inside each x value, that's a reflection across the y-axis. Remember, reflection across the x-axis is going to change everybody's sign. Reflection across the y-axis is only going to change the sign of the odd-powered terms. And then that's what we see in there, number 18. It's only changing the sign of the x to the third and the x. The x squared and then the constant stays the exact same sign. And then here's number 19. It's a vertical stretch by 2. And we can confirm that. We see that it is stretched out this long ways by 2. You just multiply everything by 2. Right? Remember, and that we kind of talked about that before when we talked about how many zeros it has, and removing the GCF of just a number does not change the zeros, right? And when we created the function, we created that simplest function. We multiplied everything out. We created the polynomial, and then you could potentially multiply it by any factor, and it would not change the amount of zeros, because look, we see how the x-intercepts are not changing, even if I multiply the whole function by 2. Okay, so there's through 19. There's 20 and 21. Again, you didn't need the graph. I'm just showing it there to confirm what we think happened. The 1/2 f of x is a vertical compression, so it should look like this, like compressing toward the x-axis, and that's what happened. 1/2 times f of x is 1/2 times that whole 2x to the 4th minus 8x squared minus 2. So it's x to the 4th minus 4x squared minus 1. Now, 21 is something horizontal, and that's where it starts to get a little bit more tricky. Because I do have to put something inside the parentheses, I've got to take that power to all parts inside the parentheses. Especially if it's a product there, I can distribute the power, and it's a little bit easier than doing it left or right. All right, so we bring in the 4th power. 1/2 to the 4th power is 1/16. So 1/16 times 2 is 1/8. Minus 8 times 1/2 squared would be 1/4. So 8 times 1/4 is 2. So minus 2x squared. And then the minus 2 on the end, the constant does not change. So we know it's a horizontal stretch by a factor of 2. Make sure you wrote that. Make sure that you wrote a horizontal stretch by 2, not a horizontal compression by 1/2. That's not the case. Remember, it's always the reciprocal of the value that goes on the inside. So it's 1/2 turns into 2. And that is the factor, so therefore, since it's bigger than 1, it's a horizontal stretch. And then here are numbers 22, 23, and 24. Number 24, a reflection across the x-axis is the negative f of x. And so they're kind of putting it all as one. I wish they would have separated that out a little bit, but they kind of did, because you can kind of see it as one step with the negative coming in with the plus. But then we put in the x plus 3. That's the left 3. So you see it reflecting across the axis and then going left 3. So we see the x plus 3 inside the parentheses, and then we just have to take that to the 4th power. Don't forget, don't drop the negative. If your signs are off, you must have dropped the negative for the reflection somewhere along the way. And if you accidentally got, what would that have been in the end? Minus 81, then you somewhere along the line dropped the 6. Yeah. And that's where the mistakes generally come to pass. Usually it's right here, right at the end, or dropping that negative. You work so hard on taking that x plus 3 to the 4th power, which, okay, good. That is difficult to do, but you drop the other pieces. You drop the negative at the front. You drop the plus or minus at the end. You got to be careful with that. Number 23, vertical compression, and then a vertical shift. Okay, 2 vertical things, nice and easy. I got a times f of x, which is the 1/3 times f of x, and also by the vertical shift is plus 1. So we got to multiply by the 1/3 first, which is that 1/3 x. It should have been minus 2, 1/3 x minus 2, 1/3 x to the 4th minus 2, and then we add the 1, so it should be 1/3 x to the 4th minus 1. We see it confirmed there on the graph. And then there's number 24. The answer for 24 is 1/16 x to the 4th minus n. All right, how did we do on this whole transformation stuff? We do all right? Again, I think we would all agree that the most difficult piece of this is moving something left or right. Beyond that, it's moving something horizontally, right? Whether it's horizontally stretching, compressing, horizontally shifting, that's the hard stuff. The vertical stuff is pretty easy. Just multiply it all by something for vertical stretching, compression, or add it all by something. Add something to the end, which is a vertical shift. Any other questions before we get to today's notes? No? Okay. Let's get to it then. The last section out of chapter 6. Holy cow, we've been in chapter 6 for a while. It feels like forever. Like, think back to when we did that whole choice board thing. That was the beginning of chapter 6. Does that seem like a long time ago?
It seems like last week.
I thought I was going to keep going. Oh. That's okay. There's an attempt you right up on the top. I think it's the leave it on the right side of the top. Was I correct? Is that one? All right, so section 6.9 is curve fitting with polynomial models. Ooh, something. Curve fitting with polynomial models. Okay, again, another topic that we have done before. We have done curve fitting, but now we're going to be talking about it in terms of polynomial models. Curve fitting with polynomial models. We've already done curve fitting with linear models. Now, remember with linear model and quadratic models. Now, remember with linear models, I was looking at a constant change in x as it corresponds to a constant change in y. With quadratic models, I said, okay, constant change in x, but I had to look at the second differences within the y values to see if it was quadratic, right? I would have to see a constant second difference to see if it was quadratic. Take a look here. Take a look at those years in that table as it corresponds to the price. The table shows closing value of a stock index in the first day of trading for various years. Okay. Now, to create a mathematical model for the data, you will need to determine what type of function is most appropriate, right? It's not easy to see what model is most appropriate, right? It's not very easy to see what model is most appropriate here, especially when you're working with something like a stock, right? Because it's going all over the place, right? We're not really sure what's going on. To create a mathematical model for the data, we'll need to determine what type of function is most appropriate. In lesson 5.8, we learned that a set of data has a constant second set of differences, could be quadratic. Finite differences can be used to identify the degree of any polynomial from a set of data. Now, this is the table that you have in front of you here. This is the sets of differences. Whenever it turns to be constant, it would be this type of function. Like, okay, we looked at the first differences when it was linear, right? Constant change in x corresponds to a constant change in y. So therefore, if I see the constant change in y with, just going from the y values, then it would be linear. But then I said, okay, if it was quadratic, it would be a constant set of second differences. You find the differences within the differences. And then that would be quadratic if it was constant. And then if it wasn't quadratic, you'd find the differences within the differences within the differences. And then it could be cubic. And then, but if it's not cubic, we could keep going on this list, depending upon how much data we had. Now, if we ran out of data, we wouldn't be able to see. Okay, we wouldn't really know for sure. But usually, in our circumstances here, we have enough data to see. All right, so use the finite differences to determine the degree of the polynomial that best describes the data. All right, so the first thing I'm going to do is figure out what my first differences are. Because if it's constant on my first differences, I know that it's linear. All right, so how much am I changing going from -2 to 4.3? I'm going up 6.3 units, right? Okay, so from 4.3 to 8.3, it's a positive change of 4. Going from 8.3 to 10.5, that's 2.2, right? 10.5 to 8.3 minus 2.2, yep. And then we go from 10.5 to 11.4. What's that? Up 0.9. And then we go from 11.4 to 11.5. That's up 0.1. So we can answer this question right now. Is it linear? No. Let's see if it's quadratic. Now for quadratic, I would look at the second set of differences. All right, so what am I doing going from 6.3 down to 4? Going down 2.3. What am I doing going from 4 to 2.2? I'm going down 1.8. Okay, going from 2.2 to 1.9. Or sorry, not 1.9, just 0.9. I'm going down 1.3. And going from 0.9 to 0.1. Going down 0.8. So is it quadratic? No. But now let's check to see if it's cubic. Let's check to see if it's cubic. All right, now, how much am I changing going from -2.3 to -1.8? Up 0.5. Going from -1.8 to -1.3, up 1, or just 0.5. Going from -1.3 to -0.8, I'm going up 0.5. So this confirms the fact that it is cubic. This constant set of first, second, third differences would be a cubic function. And that should work for every single cubic function, right? As long as it fits perfectly, right? This is more on like the algebraic side. If you have a table of data from a function and you don't know what that function is, if you find the third differences and they come out to be constant, then it's a cubic. Fourth differences, constant would be a quartic, and so on. Okay? Now, does real life data always match exactly to a specific function? No, right? Often real world data can be too irregular for you to use finite differences or find a polynomial function that fits perfectly. Man, it'd be nice to find a polynomial that fits perfectly to every situation. In those situations, you can use the regression feature for your calculator. Remember that the closer the r squared value is to 1, remember we were looking at the r squared value when we started talking about quadratic. When the r squared value is closer to 1, the better the fit. Right? R being closer to 1, r squared value being closer to 1, the better the fit. See, back in our linear chapter, we were like, okay, let's find the equation of the line of best fit. So we plotted our points and did our line. But then we said, okay, well, what happens if our data looks like this? And then back in the quadratics chapter, we said, oh, well, then it's probably a quadratic model. Well, what happens now if it looks like this? What type of model would you think it would be? Cubic. Got that curve to it. Probably positive odd, right? Well, what if it looked like this? Maybe it's quartic. What if the model looked like this? Maybe it's quintic. We don't know exactly what's going on. We can find the best type of function that might fit the data. Okay. The table below shows the population of a city from 1960 to 2000. Let's write a polynomial function for the data. Now, you'll notice up here on the whiteboard, and it's on Canvas as well, I ask you to scale down your x values. Could you use the x values that are in the table? Yes, that would be completely fine. But guess what? Your numbers are going to be really big. I know you guys don't like big numbers. So here's what we're going to do. We're going to let x equals 0 represent the number of years since the year 1960. So for example, this first piece of data is going to be a 0. What's the next one going to be? 10, 20, 30, 40. So we're just kind of like scaling down. And then we have to interpret it based on our results. Okay? So let's go into our calculator and plug in this data. All right, let's take a look here. Now, remember that to go in and change your lists, remember that's stat, edit. Stat, then edit. And then let's clear out our lists. I go up to L1, I'm going to hit clear, then down. I go up to L2, I'm going to hit clear, and then down. Down. All right, and now I'm going to input my data. Always double check to make sure you inputted everything incorrectly. All right, now from here, I want to plot my data. Right, I want to plot my data on my graphic calculator. So let's go into our y equals. I'm going to clear out the function that I have there, and I'm going to go up to plot. I'm going to go to plot, and I'm going to turn it on. Remember that if you're trying to graph a function, like if you're on your test and you're like, why isn't my thing graphing? Maybe your stat plot's on, and you were just trying to graph any old equation to try to see what it looks like, or, try to find the zeros or something. You turn the plot off and reset your window, and it's probably going to work correctly. All right, so we turned our plot on because we're looking at data. And now we're going to do zoom stat. Zoom stat. Zoom 9 for me. Zoom stat. That's going to put my window to look something like that. Okay. All right. Now I have to figure out what type of regression is going to best fit my data. What type of regression is going to best fit my data? Maybe it's cubic, maybe it's quartic, maybe it's just quadratic. I don't know. It kind of looks almost like a bottom half of a quadratic. Let's see, though. Now, to do so, I'm going to go back out to my home screen. Figure out all that trig stuff. And then I'm going to go stat. And instead of hitting edit, remember, I scroll right once to calc. Now, as you scroll down, you're going to see, okay, there's our good friends, linear regression, then quadratic regression. Hey, old friends. But isn't quadratic still a polynomial, right? So I should run quadratic, but notice here, I've got a cubic regression, and then I've got a quartic regression. I don't have a quintic regression. That's the next one is just another type of linear regression. I don't know why it's just reordered as a plus bx. And then the next one past that is a natural log regression, which we'll talk about in chapter 7. But so here's what we're going to do. Since quadratic, cubic, and quartic are all polynomial, I'm going to run quadratic and see what happens. Now, you have to be seeing your R value. Is anybody not seeing their R value? No? Okay, good. I don't know if it's... Yeah, you're not? Yeah. Do you guys see the R squared value? You guys see the R squared? Okay. So we have to be seeing this R squared value. If you don't see that R squared value, sorry, I said R. If you don't see the R squared value, you need to see the R squared value. So here's how we do that. Again, everybody pay attention because this might happen to you. If your calculator dies and it runs out of battery or something, or if you need to like change your battery, I don't know. It'll reset your calculator. So to do so, you remember you go second catalog, and then you either scroll down to D or hit the D button. You want to go diagnostic on. There it is. It's back there. Second catalog is down here. And then I just hit D or scroll down to D for diagnostic, and we want to choose diagnostic on. Hit enter, make it say done, and then just rerun that regression. I think we wanted to do quadratic, right? So stat calc 5. And there's our quadratic regression. Now, let's kind of analyze our R squared value. Pretty good fit, right? 0.994, which makes sense. I said it looked pretty closely to the bottom of a quadratic. But guys, let's take a look at the other ones and see what happens. I'm gonna stat calc. I'm gonna choose choice 6 now for a cubic regression and see what happens. Ooh, look at that R squared value. Ooh, even better. I wonder if it gets even better with quartic. Let's see. Stat calc. Whoa. Stat calc. Now, notice on my screen, I don't have enough lines to see all my entries. It's a 1. What does that mean? It's a perfect fit. It is a perfect fit. So, I have to figure out which one is the best to use. Well, which one is the best to use? The quartic regression. Okay? So what does that mean? Well, remember that the variables that it's listing out for you, the A, B, C, D, whatever, those are just the coefficients on your quartic regression. So your actual equation is y is equal to 6.25 e to the negative fifth. Come on now. Let's not do scientific notation in there. That would be 0. Okay. 1. Gotta move it 4 more places. 1, 2, 3, 4. 625. X to the 4th plus 0.0996 x to the 3rd minus 2.716 x squared plus 108.942 x plus 4,267. So that's my equation that best models that data. That's my equation that best models that data. Now, does it ask me anything beyond that? No, I mean, I could answer questions beyond that. I could say, okay, based on that model, when is the population going to exceed, let's go crazy, 50,000. When is that population going to exceed 50,000? Well, is 50,000 an X value or a Y value? It's a Y value, right? The population was the Y value. So I would go into my Y equals and say, okay, I never plugged in my equation. Oops, sorry. I never plugged in, I guess I got to plug in my regression. So when I go to my regression, I'm going to go, remember this, to put it into Y equals, you go vars, statistics, choice 5, scroll right twice to EQ to put it in there. And now this is nice because it puts the whole thing in there. I don't even have to like retype it in.
Where's E?
What's that?
This one?
I can't see your calculator. You said this one.
That one right there?
EQ. EQ on top.
Oh, you do.
EQ. And now we said, okay, 50,000, right? 50,000. When is the population going to reach 50,000? I'm going to graph this. Now I see my equation coming across. Am I really going to see my 50,000 line? I doubt it. So I might have to, remember, zoom fit. You got to kind of, manipulate your window a little bit, see what works best. Let's try zoom fit. Let's see if I can see the intersection point with zoom fit. Oh, wow. I'm way off. Let's zoom out a little bit. Zoom 3, enter. Ooh, this might do it. Oh, there it is. Okay, I'm going to second calculate my intersection point now. Okay, so I just made this up. I said to get to be population of 50,000, it's going to take 80 years, 80.49 years. So what would that be? What's 80 years past 1960? 2040? So that's what they believe the population to be. Okay, based on this model. Let's do a different one. The table below shows the opening value of a stock index on the first day of trading in various years. Use a polynomial model to estimate the value on the first day of trading in 2000. You know what? Why not? Let's make that 2020. 2021. I don't know how this is going to come out. Hopefully it's going to come out good. Let x equal 0 correspond to the number of years since 1990. Nice round number. Okay, so that means my x values here for the year, that's going to be a 4, a 5, a 6, a 7, an 8, and a 9. All right, so that I go into my calculator and I go to my stat edit, and I'm going to clear out my list now. Clear out list 1, clear out list 2, and I'm going to plug in my data. Six pieces of data. Three, 652, 948, 1506, 863, 901, 4, 5, 6, 7, 8, 9. Okay. Let's see which model best fits my data. I'm going to go, I'm going to quit out to my home screen, and let's run stat calc 5. Okay, R squared value for stat calc 5 for quadratic. Meh. Stat calc 6, cubic regression. Okay, a little bit better. Stat calc 7. Let's see. Okay, the R squared value. Okay, that's respectable. 0.89. Looks like I'm going to be using the quartic regression again. Okay, and again, that was, I'll write it in there, 0.89. R squared was 0.89. So that's why I want to use quartic regression, because of the good R squared value. So my model would be, since it's a quartic model, we would say y is equal to 32.23 x to the 4th minus 854.8 x to the 3rd plus 8,233.2 x squared minus 33,944.82 x plus 51,198.57. All right, so now what I do is I go into my calculator, into my y equals, make sure my stat plot's on. I'm going to clear out my y equals stuff, and now I want my new regression to go in there. Bars. Bars, then statistics, then scroll right twice to EQ. Okay, now I'm going to zoom stacked to get this to go in. Now, what do we see about the data? It's kind of spread off that line, isn't it? Yeah. Okay, so based on this model, let's try to figure out what the price is going to be in 2021. Now, am I going to plug in X? No, we would all agree that the year is the X value, correct? The year is the X value. What am I going to plug in for my X value? Am I going to plug in 2021? What am I going to plug in? 31. Because I said let X equal 0 correspond to the number of years since 1990. That means I've got to say, okay, 31 years past 1990. Right? So I'm going to go, and because this is an X value, this is a little easier. I can say, second, calculate the value of 31. Uh-oh. What do I do? Zoom out. When in doubt, zoom out. I've got to see 31 on my screen. I'm not sure if I'm going to see 31 on my screen still. Let's see. Second count value of 31. Oh, I got to zoom out again. You know what? I could, at this point, I could zoom out. But let's just go in and manipulate our window. Let's say, okay, I want my X maximum to be, I don't know, 35. There we go. Oh my gosh. This is going to be giant. Second, calculate value of 35. Holy cow, that's a lot of, hopefully we bought this stuff. Did I say 35?
Yeah.
I meant 30. I meant 31, didn't I? Second, calculate the value of 31. That's much better. Here, we'll just overwrite that. There we go. So if I had bought this stock, the price would be, okay, let me put commas in. This year, $11,209,953 per share. Per share. I think it probably would have come out a little bit more reasonable if I stuck with the books. Like, see what happened in 2000. Okay, questions about that? No? We good there? Okay. I'm going to stop the video and give you some time to work on your homework. So long, everybody at home. Shout out, Holly. Shout out.